What if time didn't just move forward? What if somewhere in the laws of the universe the flow could reverse and we might never even notice? Today, we'll journey from Newton's clockwork cosmos to Einstein's space-time, from the arrow of time to the strange possibility of its undoing. If the mysteries of time stir your curiosity, hit like, subscribe, and share your thoughts in the comments, because in this story, your perspective is part of the discovery.
Time is the river that carries all things forward. It begins without our consent, sweeps us along without pause, and ends without our permission. Moments rise and vanish like foam on its surface. A glass shatters on the floor and never leaps whole into the hand again. A flower opens in the warmth of spring, but never curls back into its bud. Stars are born in clouds of fire, but never unborn into silence. This forward motion feels absolute, inevitable, the very definition of reality. Yet hidden within the mathematics of nature, time is not as loyal to its direction as it seems. In the equations of physics, the gears of reality can turn forward or backward. The river can flow the other way. If it did, life itself would become a different language. Breaths would be drawn back into the lungs before they were exhaled. The final heartbeat would precede the first cry. Galaxies would spiral inward, their light falling not outward into the night, but back into the darkness from which they came, collapsing into singularities as if history were being unwritten. And in such a world, memory would not recall what has been, but what is yet to come. Time, that most familiar of companions, remains the least understood. Physicists can chart its measure to the trillionth of a second, yet cannot explain why it should flow at all, nor why it must flow forward. In the silent logic of the cosmos, nothing forbids it from reversing. It is only we, the passengers, who assume the river's course is fixed.
Long before time was treated as a mystery, it was treated as a certainty. In the age of Isaac Newton, the universe was imagined as a perfect mechanical clock, wound once by the Creator, ticking in flawless rhythm for eternity. In Newton's vision, time was absolute. It flowed independently of the events within it, like a vast invisible stage upon which the drama of the cosmos unfolded. Whether a planet orbited the sun or stood still in darkness, time would march forward at the same unwavering pace. This clockwork view fit well with the great revolutions of classical physics, the motions of planets, the swing of pendulums, the fall of an apple, all obeyed laws that were as true yesterday as they would be tomorrow. And in these laws, there was no preferred direction. If the velocity of every particle in Newton's equations were reversed, the events would simply play backwards, yet the mathematics would hold perfectly. The universe, in theory, could run either way. It was Albert Einstein, 2 centuries later, who shattered the stage on which Newton's universe was set. In 1905, and later in 1915, Einstein's theories of special and general relativity revealed that time was not separate from space at all, but part of a single woven fabric, space-time, that could stretch, curve, and twist under the influence of mass and energy. Time was no longer an unchanging river outside the world. It was a current shaped by the very matter within it. Yet even Einstein's elegant equations remained indifferent to time's direction. They allowed for universes flowing forward and universes flowing in reverse. It was not until the mid-20th century that the arrow of time would be named. In 1927, British astronomer Arthur Eddington wrote of time's arrow, a one-way motion embedded in the order of nature. Unlike the symmetrical laws of mechanics or relativity, this arrow pointed only from past to future. Eddington noted that though the microscopic equations of physics were reversible, our experience of time was not. A broken egg would never reassemble. Smoke would never gather itself back into the match. The arrow was obvious in experience, but puzzling in theory. The clue to this asymmetry had been forming decades earlier in the work of Ludwig Boltzmann. In the late 19th century, Boltzmann sought to explain the second law of thermodynamics, the principle that in any closed system, entropy, or disorder, tends to increase. He imagined the universe not as a perfect mechanism, but as a restless sea of countless particles colliding and moving in endless chaos. Order in such a system was fragile, an improbable arrangement of particles that would, over time, break down into more probable, disordered states. This statistical view reframed time itself. The forward direction we experience, Boltzmann suggested, might simply be the direction in which entropy increases. Looking forward in time meant moving toward greater disorder. Looking backward meant tracing improbable paths toward order. This idea hinted that time's arrow was not a fundamental law of nature, but an emergent property of probability. Yet Boltzmann's view was not unchallenged. The Austrian physicist Joseph Loschmidt posed a haunting objection, now known as Loschmidt's paradox. If the equations of motion are perfectly reversible, then for every forward-moving process, there exists a backward-moving one that is equally valid. Why then, Loschmidt asked, do we observe only the forward march toward disorder and never its reversal? The paradox remains a deep point of tension in physics. The microscopic laws of motion are symmetrical, yet the macroscopic world is clearly not. Other thought experiments sharpened the mystery. James Clerk Maxwell, one of the architects of electromagnetism, imagined a hypothetical being, later called Maxwell's demon, who could sort fast-moving molecules from slow ones, creating order from chaos without expending energy. Such a creature could reverse entropy in a closed system, apparently defying the second law of thermodynamics. If such reversal were possible, would it also reverse the arrow of time? The thought experiment revealed that entropy's growth and time's direction might be contingent, not inevitable. By the mid-20th century, physicists had mapped the terrain of the puzzle. The equations governing motion, both classical and quantum, allowed time to run either way. The universe we inhabit displayed an overwhelming bias toward forward flow, and the link between entropy and time seemed strong, but not absolute. From Newton's clock to Einstein's fabric, from Boltzmann's probability to Eddington's arrow, the question had only deepened. If the laws of nature themselves do not forbid the past from becoming the future, then why has the river chosen this direction? And more unsettling still, could it, under the right conditions, choose another?
For centuries, science had built its confidence on the idea that nature's laws were not only universal, but timeless. Gravity did not weaken in the morning and strengthen by night. The orbits of planets, the fall of stones, the dance of atoms, all unfolded under rules that worked equally well forward or backward. In the abstract realm of mathematics, a falling apple could just as easily rise from the grass, returning to its branch. A cloud could gather back into the cup of a teapot. And yet, outside the blackboard, such reversals never happened. The realization was as quiet as it was unsettling. The laws of physics do not care about the direction of time. In Newton's equations, if the velocities of every particle were inverted, the clockwork universe would simply run in reverse. In the quantum world, Schrödinger's equation, the foundation of wave mechanics, is equally blind to direction. Even Einstein's general relativity, with its elegant curvature of spacetime, permits solutions where events unfold in both temporal directions. This symmetry is called time reversal invariance, and it is one of the most profound tensions in all of physics. On paper, reality has no preferred direction. In experience, it does. The shock came in recognizing that the arrow of time is not written into the fundamental laws. It is something else, something emergent, perhaps even fragile. For a physicist trained to believe in the absoluteness of nature's rules, this was a wound to the very idea of certainty. It meant the universe we see is not the only one that could exist. Another, identical in every equation, could be playing out in perfect reverse. Every birth, a death. Every cause, an effect that comes after. The paradox deepened in the realm of thermodynamics. The second law states that in any isolated system, entropy, the measure of disorder, must increase. It is the bedrock reason why time seems to flow forward. Broken glasses do not reassemble. Cold tea does not heat itself. But here lies the contradiction. This law is statistical, not absolute. At the microscopic level, the molecules that make up a broken glass could, in theory, collide in exactly the right ways to restore it whole. The probability is unimaginably small, so small it may not occur once in the lifetime of the universe, but it is not zero. This statistical nature means entropy's growth is not truly a law in the same way as gravity. It is an overwhelming tendency. And tendencies can, in principle, be reversed. The thought that entropy's one-way march is not a fundamental truth, but a cosmic habit, was deeply unsettling. The discomfort sharpened in 1964 when particle physicists uncovered something even stranger. While studying the decays of subatomic particles called kaons, James Cronin and Val Fitch found that the process violated CP symmetry, the combined reversal of charge and parity. Through the mathematics of quantum field theory, such a violation implied a violation of time symmetry as well. Nature, at this microscopic scale, seemed to have a faint preference for one direction of time over another. This was not a sweeping reversal of the laws. The effect was vanishingly small and limited to certain rare particle interactions, but it was enough to show that time's arrow was not merely an illusion of human experience. Something deep in the quantum fabric was tilted ever so slightly toward the forward direction. And yet, this discovery only intensified the mystery. If time reversal can be broken at the smallest scales, why does it not show up in the rest of physics? Why is the violation so tiny compared to the vast unidirectional flow we see in everyday life? Is our universe's forward arrow the sum of such quantum biases, amplified over cosmic history, or does it arise from a different source entirely? The questions multiplied. If the fundamental equations allow both directions, and if tiny violations of symmetry exist, then is time's forward march the result of a cosmic choice? Perhaps one made at the moment of the Big Bang? In the split second after creation, when the universe was unimaginably hot and dense, could its conditions have locked in a single direction for the arrow of time? And if so, could another universe have chosen differently? Such thoughts were not idle speculation. Mathematical models of cosmology suggested that if the universe began in a state of minimal entropy, as the smooth, uniform glow of the cosmic microwave background implies, then entropy's growth would be inevitable thereafter. But nothing in physics demanded that the beginning be so smooth. It could have been rough, chaotic, high in entropy from the start, in which case time might have no direction at all. In laboratories and lecture halls, the shock of this realization was philosophical as much as scientific. It hinted that the arrow of time might not be woven into the foundation of reality, but drawn like a chalk line on the surface, a line that could, under the right conditions, be erased or redrawn in the opposite way. And if that were true, then the idea of before and after, the very grammar of reality, could be nothing more than a feature of this particular cosmic arrangement. In another, the grammar could read backward.
Once the shock had settled, the pursuit of time's mystery turned from philosophical unease to experimental precision. If time's arrow was not absolute, and if its direction was shaped by hidden rules, then those rules might leave fingerprints, subtle marks in the data that could be measured, tested, and perhaps bent. The search began at the smallest scales. In the underground halls of particle accelerators, beams of matter collided at near-light speeds, momentarily recreating the conditions of the early universe. Physicists returned to the phenomenon that had cracked open the door to asymmetry, the fleeting violation of time reversal in the decay of unstable particles. Kaons and B-mesons became the messengers of this hidden bias. At facilities like CERN and Fermilab, detectors the size of buildings recorded their disintegrations in exquisite detail. Each event was a microscopic drama, a particle transforming into lighter fragments, governed by quantum probabilities. But hidden in those transformations were patterns, minute imbalances that whispered of time's preference. The symmetry between forward and backward decay, though almost perfect, was not exact. Like a perfectly balanced coin that lands heads ever so slightly more often than tails, the subatomic world seemed to lean, however gently, toward the future. Even so, the lean was not enough to explain the universe's overwhelming temporal order. The gap between quantum hints and cosmic certainty remained as wide as ever. So the search expanded, outward, into the stars. Astronomers looked to the sky not just for light, but for age. Every photon carries a timestamp, the story of its journey through space and time. The cosmic microwave background, discovered in 1964, became one of the most valuable of these records. Its faint, ancient glow, the afterlight of the Big Bang, was astonishingly uniform, varying by only a few millionths of a degree across the entire sky. To cosmologists, this smoothness was the key to time's arrow. It suggested that the universe began in an extraordinarily low entropy state, from which disorder could only grow. Yet here again, the question sharpened. Why did it begin that way? Low entropy at the start is not demanded by any physical law. It is an initial condition, a fact that seems to stand outside the rules. If the early universe had been high in entropy, the distinction between past and future might never have arisen at all. In that alternate cosmos, time could meander aimlessly, or flow in both directions, or not exist in any familiar sense. Between the smallest particles and the largest cosmic structures, physicists began to notice patterns that defied classical intuition. In the quantum realm, certain systems behaved as though time had no direction at all. The equations describing an electron's wave function made no distinction between forward and backward solutions. Both were equally valid in the abstract. Only when the particle was measured, when probability collapsed into a single outcome, did the arrow reappear. This raised a troubling possibility. Perhaps time's flow is not a universal feature, but a local illusion, emerging only when complexity and observation intervene.
The deeper one went into the quantum vacuum, the more the boundary between past and future dissolved. In the last decades, new tools have begun to push this investigation further than any before. The Large Hadron Collider has not only confirmed tiny time symmetry violations, but is probing whether such biases might have played a role in the imbalance between matter and antimatter after the Big Bang. If matter had not ever so slightly outcompeted antimatter, the universe might have annihilated itself in a flash of radiation, leaving no atoms, no stars, no observers to ponder time at all. Meanwhile, space observatories like the James Webb Space Telescope have been tasked with peering back across billions of years toward the cosmic dawn. By studying the earliest galaxies and their structures, astronomers hope to trace the flow of entropy across cosmic history, to see whether the arrow's strength has remained constant or shifted over time. Other instruments turn to the most violent events in the cosmos, the collisions of black holes and neutron stars. These cataclysms send ripples through space-time itself, gravitational waves, which LIGO and Virgo can now detect. In principle, the symmetry of these waves could reveal whether space-time itself carries a built-in bias for forward motion, or whether the arrow is imposed only by thermodynamic processes within it. In parallel, theorists continue to explore the possibility of time-symmetric cosmologies, models in which our universe was born not alone, but alongside a mirror twin. In such a scenario, the Big Bang would be the middle point, not the beginning. To one side, our universe expands forward in our time. To the other, a mirror universe expands forward in its own reverse time. From our perspective, their history would be our future, and ours would be theirs. This idea is more than poetic symmetry. It is mathematically consistent with certain models of general relativity and quantum cosmology. And if such a mirror exists, its existence would mean that time's arrow is not a universal law, but a local orientation, like the polarity of a magnet. These lines of evidence, data, and speculation have not yet converged into an answer, but the investigation has transformed the question itself. The old inquiry, why does time move forward, is giving way to a stranger one. Is forward even a property of time at all, or is it simply the name we give to the direction in which entropy increases in our corner of the cosmos? If that is true, then under the right conditions, perhaps in the depths of a black hole, or in the final seconds before a cosmic rebirth, the arrow could turn. And if it turned, the story of the universe would not end. It would be told again, in reverse.
In science, there are moments when a question stops being a puzzle and starts becoming a threat, not to life, but to the foundations of understanding itself. The investigation into time had begun with Newton's certainty, been shaken by Einstein's curvature, and cracked open by the unsettling symmetry of microscopic laws. But here, the inquiry crossed into stranger territory, into ideas that felt less like explanations and more like the unraveling of reality itself. For if time could flow backward, even in principle, the consequences were not simply theoretical. They struck at the heart of causality, the chain of cause and effect that gives order to every event in the cosmos. Reverse the chain, and every link snaps into paradox. Physicists call these contradictions causal loops. In a universe where effects can precede causes, one could imagine a signal sent into the past, received before it was sent, influencing the very choice to send it. Push the logic further, and the grandfather paradox emerges. An action in the past that prevents the future in which it was taken, erasing the actor entirely. Mathematically, these loops are allowed by certain solutions to Einstein's field equations. Physically, they seem to defy the coherence of reality itself.
Yet the strange truth is that relativity does not forbid them outright. Within its curved geometry of spacetime, there exist possible structures known as closed time-like curves, paths through the fabric of the universe that return to their own starting point in time. Such curves could, in theory, be created near extreme gravitational objects where spacetime is twisted almost beyond recognition. The speculation becomes more unsettling when applied to black holes. In the deepest layers of general relativity, a rotating black hole, a Kerr black hole, contains regions where time and space trade roles, where the concept of forward time becomes ambiguous. In such places, it is not impossible to imagine an arrow of time that points inward for one observer and outward or backward for another. Beyond relativity, cosmology itself offers scenarios where the arrow might flip entirely. Some models suggest that the Big Bang was not the ultimate beginning, but a turning point between two mirror universes, one expanding forward in our time, the other expanding forward in its own, reversed time. From our perspective, their expansion would look like contraction, their future, our past. If this is true, the arrow of time is not universal, but relative, a feature of orientation, like north and south. The Big Bang would then be the equator of time, with two opposite arrows pointing away from it into two mirrored realms. The implications reach into the philosophy of existence itself. In such a framework, death and birth are not final boundaries, but simply transitions along a path that curves back towards origins. The end of our universe, whether in heat death, collapse, or some quantum phase change, could be the beginning of another, flowing the other way. And yet, the mystery deepens even further when consciousness is drawn into the picture. Our memories are built upon sequences of events. Our very sense of self depends on cause preceding effect. If the arrow of time were to reverse, would a conscious mind experience the reversal, or would it simply adapt, remembering what, from our point of view, has not yet occurred? Would we notice time's inversion, or would we live it as naturally as we live its current flow? This question touches the edge of an unsettling thought. Perhaps there are already regions in the cosmos where the arrow runs differently. The universe is not a uniform stage. In its most extreme environments, near event horizons, in the quantum froth at Planck scales, space-time behaves in ways that defy ordinary sequence. In such places, it is not impossible that local reversals of time might occur, invisible to us except in the subtlest of signatures. Some theorists even speculate that the arrow could fragment, that in the deep future, as entropy approaches its maximum, pockets of reversed order could briefly arise, birthing their own backward-flowing histories. In those brief and alien domains, the collapse of a star might precede its formation. The cooling of a planet might follow its ignition. The very possibility forces a reconsideration of before and after as absolute concepts. It suggests they may be conveniences of a particular cosmic state, as arbitrary in the grander picture as calling one side of a coin heads and the other tails. And here lies the deepest unease. If time's arrow is contingent, a product of conditions, not a fundamental law, then the inevitability of the future is an illusion. What we call the past may not be fixed forever, but fixed only from within our arrow's frame. From another vantage, one inaccessible to us, it might be fluid, mutable, even undone. In the laboratories and observatories of the world, such thoughts remain carefully fenced by mathematics and theory. But in the mind of the physicist and the listener, they carry the same quiet dread. The story of the universe may not be a straight line from birth to death, but a loop, a mirror, or a braid of timelines twisting in ways we cannot yet imagine. The investigation no longer asks simply whether time could flow backward. It asks whether backward and forward are real distinctions at all, or merely the orientation of a deeper, hidden structure in which the entire history of the cosmos is laid out, all moments existing at once, like pages already printed in a book we have yet to read.
In the quest to understand time's arrow, science has reached a strange crossroad. The hard numbers of physics do not demand that time must always flow forward. The deeper we look, the more we find loopholes, cracks in the one-way wall of reality. Some cracks are narrow, no more than mathematical curiosities. Others gape like doorways into universes we can barely conceive. From these openings, a handful of theories emerge, each daring to suggest how time might, under certain conditions, flow the other way. Number 1. Entropy reversal, the thermodynamic rebellion. At the heart of our sense of time lies the second law of thermodynamics. In a closed system, disorder, entropy, always increases. This relentless increase gives time its direction. A shattered glass does not reassemble. A burnt log does not unburn. But the law is statistical, not absolute. In rare cases, vanishingly rare, random fluctuations can cause order to rise instead of fall. Theoretically, in an infinite expanse of time, every possible fluctuation will occur. This means that somewhere, somehow, a broken egg might spontaneously reform. And on cosmic scales, an entire region of space might experience entropy running in reverse. In such a region, the arrow of time would flip. To us, it would look like a movie playing backward. Stars forming from ashes, galaxies unwinding into gas. To the inhabitants of that region, if any could exist, life would proceed normally, their memories building in what we call the wrong direction. Some cosmologists even suggest that our universe's arrow began this way, as a low-entropy fluctuation in a sea of chaos. If so, the end might be just as arbitrary as the beginning, a moment when entropy's march stalls, reverses, and history runs uphill once more. Number 2. CPT symmetry, the mirror universe. Physics has a strange love for symmetry. One of its deepest principles, CPT symmetry, states that the laws of nature remain unchanged if three things are reversed at once. C, charge, particles replaced with their opposites; P, parity, left and right swapped; and T, time, run backward. Mathematically, a universe with opposite charge, mirrored space, and reverse time is just as valid as ours. It would be a perfect reflection, a cosmic twin. In this model, the Big Bang was not the start of a single timeline, but the meeting point of two. One arrow of time points away from the bang. That's us. The other points in the opposite direction, a universe expanding into what we call the past. From our perspective, their time flows backward. From theirs, ours does. Neither is wrong. Both are complete, separate realities. If CPT symmetry truly governs all physics, then backward time is not exotic at all. It's simply the way half the cosmos already works, forever hidden beyond the opaque curtain of the Big Bang. Number 3. The Wheeler-Feynman absorber theory, the two-way conversation. In the 1940s, physicists John Wheeler and Richard Feynman proposed a radical idea about light. What if electromagnetic waves travel not only forward in time, but also backward, equally and naturally? In their absorber theory, when an electron emits a photon, that photon's existence is tied to both the emitter and the absorber.
The process is a handshake across time. The emitter sends a wave forward, the absorber sends one backward, and the event happens only when both agree. If true, this means that time's flow at the microscopic level is not a one-way broadcast, but a conversation. Messages exchanged both to the future and the past. While this doesn't create paradoxes on its own, it hints that information might already travel in ways that ignore the arrow entirely, hidden in the quiet chatter of the quantum world. Number 4. The block universe. Time as a landscape. Einstein's relativity led to a profound, unsettling image of reality, the block universe. In this view, time is not a river. It is the entire landscape already laid out. Past, present, and future are all equally real, like different coordinates on a map. In such a cosmos, time doesn't flow at all. The sense of motion is an artifact of consciousness, our minds moving along a fixed path through the four-dimensional block of spacetime. Backward time, in this picture, is simply a matter of perspective. A being with a different orientation in spacetime might experience our past as its future. All of history, forward or backward, is already there, waiting to be experienced. This model offers no mechanism for changing the past, but it quietly erases the idea of the past being gone. It's all still there. Every heartbeat, every falling leaf, etched forever into the geometry of reality. Number 5. Cosmological time reversal. The bounce. Some cosmologists believe our universe will not end in heat death, but in a great collapse, the Big Crunch. In certain models, this collapse does not end everything, but triggers a bounce, a new expansion, perhaps with reverse time's arrow. The bounce could be symmetrical. Our future is another universe's past. Or it could be asymmetrical, with subtle differences between the cycles leaving faint traces in cosmic background radiation. If the bounce model is correct, we may be one in an infinite chain of universes, each alternately running forward and backward, linked by the turning points of their births and deaths. Number 6. Quantum time loops, the many worlds escape. In quantum mechanics, particles can exist in superpositions, many possibilities at once, until measured. This strangeness opens the door to closed time-like curves in certain theories of quantum gravity. If a particle could loop back to an earlier point in time, it might create paradoxes, unless the universe resolves them by splitting into parallel histories. In this many worlds view, going back in time doesn't change your past. It simply moves you into a different branch of the universal wave function, where events unfold differently. Backward time becomes less like rewinding a film and more like stepping sideways into a new reel, a reality where you can walk into your childhood home, but the person who grew up there is not quite you. Across all these models, one truth emerges. Backward time is not forbidden. It may be rare, it may be hidden, it may be accessible only in ways that preserve the deeper consistency of reality. But the laws of physics, as far as we can tell, do not close the door. Whether it exists in the flicker of quantum events, in the mirror of another universe, or in the vast arcs of cosmic cycles, backward time is a possibility our equations refuse to erase. And perhaps that is why the question feels so alive. It is not a fantasy. It is a mirror held to nature. And in that reflection, we may see ourselves walking not just into the future, but into the past, step by step, forever.
Under the cold ticking of Newton's cosmic clock, time was imagined as an unbroken thread, measured, predictable, and absolute. In his 17th century universe, the hands of the celestial watch swept forward with unwavering certainty, indifferent to human perception. The planets traced their orbits like gears in an immense mechanism, and time itself was the steady drumbeat to which all reality marched. For centuries, this vision reigned unquestioned, until the early 20th century, when Albert Einstein shattered the clock and replaced it with a pliable fabric, spacetime. In his relativity, time was no longer a universal metronome, but a dimension woven together with space, bending under the weight of mass and energy. What was once fixed now became relative, slowed by gravity, stretched by velocity. The old certainty fractured. Yet, for all its elegance, relativity offered an unsettling implication. The equations did not favor a forward march. They were symmetrical, like a mirrored river, able to flow in either direction. In the language of mathematics, past and future were interchangeable. It was Arthur Eddington in the mid-20th century who coined the term the arrow of time. He noted that while the laws of physics might be reversible, our experience was not. A cup falls and shatters, but never leaps whole from the floor. A candle melts, but wax never reassembles itself into a pristine taper. Something, subtle but unyielding, drew the arrow in one direction. Ludwig Boltzmann had sought that something decades earlier. In the 19th century, he peered into the microscopic chaos of gas molecules and found a statistical truth. Disorder, entropy, tended to increase. Time's arrow, he proposed, was born not from the laws themselves, but from probability. Still, questions festered. James Clerk Maxwell's thought experiment of a demon sorting particles and Loschmidt's paradox challenging entropy's inevitability whispered the same provocation. If the microscopic rules allow reversal, why is the macroscopic world so stubbornly one way? It was here, between certainty and doubt, that the modern mystery of time began.
Time is not merely a measurement. It is the quiet architecture of human existence. It shapes every heartbeat, every sunrise, every shadow that lengthens across the floor. It is the silent current beneath our lives, carrying our childhood away from us, pulling us toward the faces we have yet to meet, and, ultimately, toward the horizon from which there is no return. We know it through memory. The fragile film of the past we spool endlessly in our minds. We feel it in the weight of aging, as the mirror slowly trades youth for lines and light for shadows. We see it in the cycles of the world, the tide retreating, the leaf falling, the star exhausting itself into cold. To be human is to be shaped by the one-directional march of moments, and yet we cannot help but wonder. If the current were to reverse, would we notice? If breath came before speech, if grief came before love, if endings became beginnings, would our miles too reverse their logic? Would the story still feel like a story, or would we simply live it without knowing anything had changed? Perhaps, in such a reality, what we call backward would be indistinguishable from forward. Perhaps direction itself is an illusion, born not from the universe's structure, but from the way consciousness filters it. Our sense of time could be no more fundamental than a shadow is to light, an artifact of perspective, not the essence of reality. There is a haunting thought in this, that we might already inhabit a world where time flows in ways we cannot perceive, folding, circling, diverging, while our limited senses trace only a single narrow line. Maybe
The true mystery is not whether time could reverse, but whether it already does. Not in the ticking of clocks or the orbits of planets, but in dimensions unbound by our comprehension. In the deep architecture of reality, where our beginnings may already lie beyond our endings, and our endings may be the quiet seeds of our birth. And so we return to the river, not a straight and final course, but perhaps a vast unseen ocean whose currents run in every direction at once. We sail it unaware, certain of our forward journey, even as the waters themselves may be carrying us into realms where forward and backward have no meaning at all.